Okay, we are resuming our discussion of the binary search algorithm. What you see on the screen is an implementation based upon the slide that I showed you. And this implementation has a couple of features you want to pay attention to. One is for debugging purposes, I'm just putting in this statement that will basically tell you what areas of the array that you're searching each time you make a call to binary search. And hopefully you will find that the distance between low and high is shrinking as we are repeatedly dividing the array into half. Okay? And so here's the code for all the stuff that you've seen. It's the same as the algorithm. And we have a test program. And the test program, I have an array. The array must be sorted. That's the requirement. And I have a bunch of keys that I'm searching for. So the first time I want to search for a 1, and let's talk about this for a moment. When I search for a 1, what's the result going to be? True or false? Well, it's going to be false. But notice that this is what we call a boundary test case, because it should appear at the beginning of this list if it's going to appear. Another test case ought to say, let's search for something that is beyond the last value. And that's this test case. We're also testing to see if we can hit the last value exactly if it's there. If we can hit the first value if it's there. We're also testing what happens when we hit the middle element, and so on. All right, so I think this is a good set of test cases. And you're able now to get this file from the public repository, and here's the name of the file, test_binarySearch, and you can run it and play with it and study and experiment with it. And here's the experiment I want you to do. All right, I want you to take this program and make 2 changes. Observe what happens and learn more about the rules about the requirement that the array be sorted and that you have breaks to stop the recursion. First thing I want you to do is comment out the first if statement. What's the first if statement? It's what I call the breaks, right? So basically we're going to remove the breaks from this algorithm and we're going to try to run it and see what happens. And don't have to tell you, the thing is going to freeze. It's going to freeze in what case? Well, it's going to freeze if you can't find anything. If what you're looking for is not in there, it's probably going to freeze. It's likely to work okay otherwise. So if you don't test things thoroughly, you might think it's working when in fact it's not. So of course, once you try that, you're going to put the brakes back into effect and move on to the second change, which is change the array in the main so that it's not sorted. Then compile and run the program and tell me what you observe when you are trying to apply binary search to an unsorted array. Right? Those are the first 2 things to try. Now, there's one last thing. Notice that this binary search is assuming that the array is sorted in ascending order. Your job is to take the test binary search program, revise the function so that it works for an array that's sorted in descending order. And you should use the test program to demonstrate that the revised function works correctly. And I want you to submit that. The assignment ID is video, all caps, algorithm, ALGM, lower case. All right? It's probably not a grader for this, but go ahead and submit it. All right. Now let's finish the discussion of binary search. All right. Because the question becomes, is this an efficient way to do it? And let me give you some numbers. If I did a linear search of 1,000,000 things, we earlier said you can expect that it's going to take, this is wrong. This is so wrong. We can expect that it's going to take 500,000 times if you did a linear search. But the number of steps in this is proportional to the log base 2 of n. Okay? So if I have 2 things, I can complete it roughly in 1 step. If I have 1,000 things, 10 steps. Watch this. If I have 1,000,000 things, it's 20 steps. Whoa, it's not 500,000, it's 20. How much would it be if it was 1,000,000,000? What's 1,000,000,000? 1,000,000,000 is 1,000 million, and it would be 30 steps. Do I need to say any more about how fast this is? What's the requirement though? The array must be sorted to use this. So if you have a sorted collection, the binary search is so much faster than a linear search. And it works extremely well when you have a large list. If you have a list of 10 things, I have to tell you, it doesn't make any difference how you search if you only have 10. When you get into thousands and millions, it makes a world of difference. That's all for this. And we